Take a breath. Settle into wherever you are right now. Feel the weight of your body against the chair, the floor, the earth beneath you. Notice the stillness, the room around you, the familiar walls, the soft sounds of the world just outside. You are here. You are present. And from this single, quiet point in space, we are going to travel together, outward and outward and outward still, until the mind stretches to places that no human eye has ever seen, and perhaps in some profound way will never fully comprehend. Welcome to Infinite Science. This is a journey measured not in miles or kilometers, but in light years, in billions upon billions of kilometers, in distances so vast that our most familiar concepts of size simply cease to apply. And at the end of this journey, at the very farthest reach of our imagination, something waits, something ancient, something unimaginably massive, something that bends the very laws of the universe around it, like fabric folding around an immense, invisible weight. We are going to visit the largest known black hole in the observable universe. Its name is TON 618. But before we can understand what that means, before we can even begin to appreciate what awaits us at the end of this journey, we must first understand where we are starting from. We must understand the Earth, the Moon, the solar system, the galaxy that holds us, the web of galaxies beyond. We must understand scale itself, because without that understanding, TON 618 is just a name, just a number, just a distant curiosity in a catalogue. With that understanding, TON 618 becomes something else entirely, something that will stay with you long after these words have ended. So let us begin, softly, slowly, here on Earth. There is something almost meditative about thinking carefully about scale, about the true sizes and distances of things. In our daily lives, we operate at human scales. We know intuitively how long a meter is, how far a kilometer stretches. We know the size of a room, a city block, a country. These are the scales our brains evolved to handle, because these are the scales at which our survival was determined for hundreds of thousands of years. But the universe does not operate at human scales. The universe operates at scales so extreme, both so small and so large, that the human brain has no intuitive framework for them. We can do the mathematics, we can write the numbers, but to truly feel what 10 billion light years means, to hold it in your body the way you hold the distance to a friend's house, that is something different, something that requires a different kind of attention. What we are going to do in this journey is build up our sense of scale carefully and deliberately. We are going to start at the smallest familiar level, the surface of the Earth, and expand outward in steps, each one larger than the last. And by the time we reach TON 618, we will have crossed so many orders of magnitude, traversed so many levels of scale that the destination will carry the weight it deserves. Let us begin with where you are right now. Imagine you are standing outside on a clear night. The air is cool and still. Above you, the sky is impossibly dark, and the stars, those ancient, patient lights, are scattered across it like grains of luminous dust on the deepest black velvet you have ever seen. You tilt your head back, you breathe, and for a moment, you feel it, the extraordinary privilege of being a conscious creature on a small, spinning world, looking outward into something larger than you can hold in your mind. That world beneath your feet, the Earth, has a diameter of about 12,742 kilometers. It is, in all honesty, a small thing by cosmic standards, and yet, from where you stand, it is everything. It is oceans and mountains, cities and forests, the entire history of human civilization, the entire web of life as we know it. Every person you have ever loved is somewhere on this sphere. Every book ever written, every song ever sung, every dream ever dreamed, all of it exists within this thin, fragile shell of rock and water and air. From space, astronauts describe seeing the Earth as one of the most emotionally powerful experiences a human being can have. The overview effect, as it has been called, is that sudden, visceral comprehension of the Earth's smallness, its fragility, the thinness of the blue band of atmosphere that separates the living world from the void. Edgar Mitchell, who walked on the moon during Apollo 14, described looking back at the Earth from lunar distance and feeling an instant global consciousness. A sense that all of humanity's divisions and conflicts and borders were absurd against the backdrop of that small, brilliant, singular world hanging in the dark. The atmosphere that wraps around the Earth, the thin veil of gas that makes all of this life possible, extends only about 100 kilometers above the Earth's surface. Just 100 kilometers. If you could drive straight up at highway speed, you would reach the edge of space in less than an hour. The sky above us is not some vast, endless expanse. It is a thin, delicate film, a whisper of gas clinging to a rock, hurtling through space. Now, let us begin to move upward. Let the ground fall away beneath you. Let the blue of the sky deepen into violet, and then into the blue-black of the upper atmosphere, and then into the utter, perfect darkness of space. Below you, the Earth curves. Its edges become visible. That iconic arc that astronauts describe as one of the most emotionally powerful sights in human experience. The clouds swirl. The oceans glitter. The thin orange line of the atmosphere glows against the black, like the rim of a lantern at night. We are 400 kilometers up now, roughly the altitude of the International Space Station. For more than 2 decades, human beings have continuously lived and worked in this orbit, conducting science, maintaining equipment, looking down at the planet they came from. From here, a full orbit of the Earth takes about 90 minutes. The crew of the ISS sees 16 sunrises every single day. From the ISS, the Earth looks both enormous and surprisingly small at the same time. It fills your view, and yet you can already begin to sense that you are in space, that you have crossed a threshold into something different. The blackness above is not the blue sky of home. It is something older and emptier. Stars do not twinkle here, they burn steadily, because there is no atmosphere to distort their light. But we have barely begun. The moon is our nearest neighbor, our companion in space. The only other world in the universe that human beings have ever stood upon, and yet the moon is not close, not by any intuitive sense of the word. The average distance from the Earth to the moon is approximately 384,400 kilometers. To put that in perspective, if you could drive a car at highway speed, 100 kilometers per hour, it would take you roughly 160 days to reach the moon, without stopping, without sleeping. A continuous 4-month drive. In the history of space exploration, only 24 human beings have ever traveled beyond low Earth orbit. They were the crew of the Apollo missions between 1968 and 1972. 12 of them walked on the moon. They remain the only human beings to have stood on another world. The last to do so was Harrison Schmitt, a geologist, and Eugene Cernan, the mission commander of Apollo 17 in December 1972. More than 5 decades have passed since any human being traveled as far as the moon. The moon itself is a world of paradoxes. It is geologically dead, its surface frozen in time, cratered by billions of years of impacts with no weather or erosion to smooth them away. The footprints left by the Apollo astronauts are still there, perfectly preserved in the fine grey regolith. They will remain there, unchanged for millions of years to come. The Moon's surface is a fossil of the early solar system. And yet, the Moon is also intimately connected to life on Earth. Its gravity stabilizes our planet's axial tilt, preventing the kind of extreme swings that might otherwise make Earth's climate far more chaotic. It drives the tides. It influenced the evolution of life. Many marine organisms evolved their reproductive cycles around the lunar tidal rhythms. The Moon is not merely our companion. In some ways, it is a guardian. We leave the Moon behind. We continue outward. And now, the Earth itself begins to shrink. That intricate, teeming, beloved world, that pale blue dot, becomes smaller. It becomes a disk, a bright blue and white circle hanging against the darkness. At the distance of Mars, roughly 225 million kilometers from the Sun on average, the Earth is a point of light, a pale dot, not even particularly distinctive among the stars if you didn't know where to look. Carl Sagan once described a photograph of Earth taken from the edge of the solar system, nearly 6 billion kilometers away, as a pale blue dot. In that image, the Earth is smaller than a single pixel. It is nearly invisible. Sagan wrote of that photograph, "It underscores our responsibility to deal more kindly with one another, and to preserve and cherish the pale blue dot, the only home we've ever known." Those words carry a particular weight now, as we begin to understand the scale of what surrounds us. The Earth is irreplaceable, not because it is central, but because it is ours. Because all of us, every human consciousness that has ever existed, has lived and died within its thin, fragile embrace. From this vantage point, looking back at the shrinking dot of home, there is something that feels like a mixture of homesickness and reverence. A love for something you perhaps took for granted until you saw it from far enough away. We continue outward. We are moving now through the inner solar system. The Sun blazes behind us, ahead of us, around us, as the center of this entire gravitational kingdom. A furnace of nuclear fire so immense that its light reaches us in about 8 minutes. And yet, even that light travel time gives a deceptive sense of closeness. The Sun is 150 million kilometers from Earth. Its diameter is 1.4 million kilometers. So wide that approximately 1.3 million Earths could fit inside it. The Sun is so massive that its gravity holds 8 planets in their orbits across billions of kilometers of space. Its gravitational influence extends to the very edge of the solar system, hundreds of billions of kilometers away. And yet, even the Sun, this colossal, roaring star at the heart of our planetary family, is an unremarkable average yellow dwarf star. Astronomers classify it as a G-type main sequence star. It sits at the middle of almost every stellar spectrum astronomers use to measure stars. Not the hottest, not the coolest, not the most massive, not the least. Massive, not the youngest, not the oldest. It is, in a sense, magnificently ordinary. One of roughly 200 to 400 billion stars in our galaxy alone. This ordinariness is, paradoxically, one of the things that makes our solar system potentially significant. We live around an ordinary star in an ordinary region of an ordinary galaxy. If life can arise here under ordinary conditions, then the universe, with its trillions of galaxies, each containing hundreds of billions of similarly ordinary stars, may be far more full of life than we currently know. But we are not here to speculate. We are here to travel. And there is much ground to cover. as we drift outward past the orbit of Mars. The red planet, smaller than Earth, with its rust-colored deserts and ancient volcanic mountains and channels carved by water that no longer flows. We enter the asteroid belt. This is a region between Mars and Jupiter, where hundreds of thousands of rocky bodies orbit the Sun. You might imagine this as a dense field of tumbling boulders, like in the science fiction films. In reality, the asteroids are so widely spaced that if you flew a spacecraft through the belt, as the Voyager and Pioneer and New Horizons probes all did, you would almost certainly never come close to a single one. Space, even within the asteroid belt, is mostly empty, mostly silence. The asteroid belt is a kind of cosmic archive, the remnants of material from the early solar system that never quite managed to coalesce into a planet. Jupiter's gravitational influence disrupted the process. The asteroids that remain are a frozen snapshot of the solar system's formation, billions of years old, largely unchanged since the dawn of planetary history. Jupiter. We arrive at Jupiter and the scale shifts again. Jupiter is the largest planet in the solar system. Its diameter is about 139,820 kilometers, more than 11 times the width of Earth. If Jupiter were hollow, more than 1,300 Earths could fit inside it. The Great Red Spot, a storm that has been raging in Jupiter's atmosphere for at least 350 years, probably much longer, is wide enough to swallow two Earths side by side. It is a vortex of wind and cloud that has outlasted civilizations, has been observed by scientists since the age of the telescope, and shows no sign of ending entirely, though it has been gradually shrinking over recent centuries. Jupiter's gravity is so powerful that the planet plays a crucial role in shaping the dynamics of the entire solar system. It acts in some respects as a gravitational shield for the inner planets. By deflecting or capturing asteroids and comets that might otherwise threaten Earth, Jupiter has helped maintain the relatively stable conditions that allowed complex life to evolve here over billions of years. Jupiter is also home to one of the most intriguing objects in the solar system, Europa. Europa is one of Jupiter's 95 known moons, and beneath its icy crust, evidence suggests the existence of a global subsurface ocean of liquid water, kept warm by tidal heating from Jupiter's gravitational kneading. Where there is liquid water, some scientists speculate, there might be the conditions for life. The possibility of microbial life in Europa's dark, deep ocean is one of the most exciting open questions in astrobiology. Beyond Jupiter, Saturn. Ringed, luminous, and impossibly beautiful. If there is a single image that captures the wonder of the solar system, something that silences even the most hardened skeptic, that makes even the most practical mind pause in something approaching reverence, it is Saturn, seen up close. Its rings stretch out in thin, shimmering sheets of ice and dust, hundreds of thousands of kilometers across, but only tens of meters thick in places. Seen from directly above or below, they form a perfect, flat disk. Seen from an angle, they create that iconic silhouette that has decorated observatory windows and spacecraft, mission patches, and the imaginations of countless people for centuries. Saturn's rings are one of the most visually spectacular structures in the known universe, and they exist right here, in our own cosmic neighborhood. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, returned images of this system of such extraordinary beauty and detail that they changed how scientists understood the complexity of Saturn's ring system. The intricate structures, the gaps and divisions, the shepherd moons that maintain the ring edges through gravitational interactions. When Cassini finally plunged into Saturn's atmosphere at the end of its mission, many of the scientists who had worked on it for decades were moved to tears. We continue. Uranus, Neptune, the outermost planets of the solar system, cold and distant, their blue hues the result of methane in their atmospheres. Neptune is so far from the Sun that its light travel time reaches almost 4.5 hours. Standing on Neptune, if standing on a gas giant were possible, the Sun would appear as little more than a very bright star, smaller than a full moon seen from Earth. You would need a telescope to see it clearly. The average distance from the Sun to Neptune is about 4.5 billion kilometers. Light takes roughly 4 hours and 20 minutes to make the journey. A human spacecraft traveling at the speed of New Horizons, the fastest spacecraft ever launched, would take about 9.5 years to reach Neptune. And yet, we are still inside the solar system, because the solar system does not end at Neptune. Beyond Neptune lies the Kuiper Belt, a vast donut-shaped region of the outer solar system containing hundreds of thousands of icy bodies, small planets, comets, and rocky icy worldlets preserved in the deep cold since the dawn of the solar system. Pluto, famously reclassified as a dwarf planet in 2006, is one of the largest Kuiper Belt objects. When the New Horizons spacecraft flew past Pluto in 2015, after a 9-year journey, it revealed a world of unexpected complexity. Mountains of water ice, plains of frozen nitrogen, complex organic chemistry, a thin atmosphere. Even at the edges of the solar system, worlds have stories. And beyond the Kuiper Belt lies something even more vast, even more remote, the Oort cloud. The Oort cloud is the outermost region of the solar system, a vast spherical shell of icy bodies that surrounds the Sun at enormous distance. The inner edge of the Oort cloud begins at perhaps 2,000 astronomical units from the Sun, 2,000 times the Earth-Sun distance. The outer edge may extend to as far as 100,000 astronomical units, halfway to the nearest star. At this distance, the Sun's gravity still just barely holds these bodies in its grip. We have never visited the Oort cloud. No spacecraft has come close. It is so remote that even Voyager 1, launched in 1977, traveling at about 17 kilometers per second, now more than 23 billion kilometers from the Sun, will not reach the inner edge of the Oort cloud for another 300 years, and it will take approximately 30,000 years to pass completely through it. Let that number settle quietly in your mind. 30,000 years. That is longer than recorded human civilization. From the first cave paintings at Chauvet, to the construction of the pyramids, to the invention of writing, to the printing press, to the Industrial Revolution, to the internet, to the spacecraft age, all of it, the entire arc of everything humanity has built and thought and written and sung, would fit inside the time it takes Voyager 1 to cross the Oort cloud. The solar system is immense beyond intuitive grasp, and yet it is just a tiny corner of the galaxy. Beyond the Oort cloud, beyond the last whispering gravitational threads of the Sun's influence, lies interstellar space. True space, the space between the stars. When Voyager 1 crossed into interstellar space in 2012, crossing scientists could identify by subtle changes in the density and composition of particles surrounding the spacecraft. It became the first human-made object to enter this realm. It took 35 years of continuous travel at more than 17 kilometers per second to reach this boundary. The data Voyager sent back confirmed what scientists had long suspected, that beyond the heliopause, the boundary where the Sun's solar wind is overwhelmed by the galactic interstellar medium, the universe feels different. The particle density drops. The environment is dominated not by particles from our sun, but by remnants of other stars. Some of them ancient, some of them long since dead. Voyager 1 is now sailing through a medium that has been shaped by billions of years of stellar evolution across our region of the galaxy. The nearest star system to our own is Alpha Centauri, a triple star system consisting of the Sun-like stars Alpha Centauri A and B orbiting each other, and the red dwarf, Proxima Centauri, orbiting them at much greater distance. Proxima Centauri, the nearest of the three to Earth, is about 4.24 light-years away. A light-year is the distance light travels in 1 year, approximately 9.46 trillion kilometers. 4 light-years is approximately 40 trillion kilometers. 40 trillion kilometers. To give that number a tangible frame, if you built a scale model of the solar system where the sun was the size of a large beach ball, about 60 centimeters across, and placed it in the center of a large park, Earth would be about 65 meters away, roughly the size of a pea. At this scale, the nearest star, Proxima Centauri, would be approximately 18,000 kilometers away. It would be somewhere on the other side of the world. This is the scale of the space between stars. It is not just large, it is incomprehensibly large. And those 40 trillion kilometers represent the shortest possible gap between stellar systems. Most stars in the galaxy are much farther apart from their neighbors. Proxima Centauri has at least one confirmed planet, Proxima b, orbiting within the habitable zone, the range of distances where liquid water could exist on a planet's surface. Proxima b is a rocky world, not much larger than Earth, completing one orbit every 11 Earth days. Whether it has an atmosphere, whether that atmosphere could support the conditions for life, whether it has liquid water, these remain open questions. But it is the closest potentially habitable world we know of, and the fact that it orbits our nearest stellar neighbor gives it a particular significance in our imagination. At the speed of Voyager 1, the fastest object ever launched by human beings, it would take approximately 75,000 years to reach Proxima Centauri. We have not yet developed the technology to send spacecraft to another star within a human lifetime. The dream of interstellar travel is real. The capability is not yet. Several proposals have been explored, from nuclear propulsion to laser-driven light sails. But none has been attempted, and the engineering challenges remain daunting. This gap between aspiration and capability is one of the quiet aches of being alive in the early space age. We have seen enough to know that the universe is full of worlds. We have not yet found the means to visit even the nearest of them. As we move through interstellar space, in imagination, the star field changes. The familiar constellations shift. The patterns we have named and told stories about for thousands of years, Orion, the Great Bear, the Southern Cross, are accidents of perspective, the result of looking at three-dimensional space from our particular vantage point. From a few light years away, the patterns would look different. Some stars would appear in new positions. New groupings would suggest themselves. The sky that has inspired human mythology, navigation, and wonder throughout all of history is unique to our location. It is our sky. The stars are not all at the same distance. They are scattered through three-dimensional space at varying depths. The constellations are flat projections of a volumetric reality. When we look at the night sky, we are seeing a compressed image of something that extends for thousands of light years in depth. The stars we see are at distances ranging from a few light years to thousands of light years, all appearing on the same two-dimensional canvas of the sky. In this interstellar space through which we now travel, the dominant sound, if sound could travel here, which it cannot because space is a vacuum, would be silence. Not the silence of a quiet room, which always contains small sounds if you listen carefully enough, but the silence of nothing. No medium for vibration, no air, no water, no solid substrate through which waves could propagate. Pure electromagnetic radiation travels through this space. Light from distant stars, radio waves from pulsars, the cosmic, microwave background radiation that fills the entire universe as a faint afterglow of the Big Bang. But these waves carry no sound. The experience of being in interstellar space, could a human being survive it, which we cannot, would be one of profound isolation. The nearest star would be a bright point of light, indistinguishable from hundreds of other stars in the sky. You would be, in every practical sense, alone, adrift in the dark. And yet, in this vast emptiness, there is something remarkable happening. Distributed across the interstellar medium, the thin gas and dust that fills the space between stars, the raw materials of future worlds are being slowly assembled. Molecular clouds of hydrogen and helium, seeded with heavier elements scattered by ancient supernova, drift and condense. In the densest regions, gravity begins to win over the thermal pressure of the gas. Pockets begin to collapse. Protostars begin to form. Out of the dark, new suns are being born. The universe is not static. It is not finished. Even in the apparent emptiness of interstellar space, the slow, patient work of creation continues. Now, let us widen our view. Let us look at the context around us, the vast, luminous spiral of our home galaxy. From far enough away, from a distance of perhaps 100,000 light-years, looking down from above the galactic plane, you could see the Milky Way as it truly is. And it is extraordinary. A flattened disk of stars and gas and dust, glowing softly against the dark. Spiral arms curling outward from a bright central bulge, like the arms of a slowly spinning pinwheel seen from above. Blue-white young stars blazing along the spiral arms, where star formation is most active. Older, redder stars gathered in the bulge at the center. Vast clouds of dark dust weaving through it all, obscuring some regions, creating the mottled, shadowed appearance that gives our galaxy its name. The galaxy of milk, the Milky Way. It is a beautiful object. From the right angle, from directly above, far enough out to see the full disk, the spiral structure is immediately apparent. The arms are not rigid, solid structures. They are regions of higher density, regions where stars are more closely packed and where the gas compression from the arms' gravitational influence triggers bursts of star formation. Stars are born in the spiral arms, live their lives, and migrate away over millions of years. The arms are self-sustaining patterns like waves on water. The water moves, but the wave pattern persists. Our Milky Way has several major spiral arms: the Sagittarius arm, the Perseus arm, the Centaurus arm, and the Orion arm, sometimes called the Orion spur or local arm, where our solar system resides. We sit about 26,000 light-years from the galactic center, in this minor, quieter spur between the larger Sagittarius and Perseus arms. The Milky Way is approximately 100,000 light-years in diameter, though its exact boundary is difficult to define precisely. Its disk is about 1,000 light-years thick. Beyond the disk, a spherical halo extends much farther, containing ancient globular clusters. Dense balls of hundreds of thousands of old stars, and dark matter, which exerts gravitational influence without emitting any detectable light. The Milky Way contains an estimated 200 to 400 billion stars, though some estimates place the number as high as 1 trillion when accounting for the many faint red dwarf stars that are difficult to observe individually. It contains thousands of nebulae, clouds of gas and dust where new stars are being born, or where old stars have ended their lives in spectacular explosions. It contains hundreds of billions of planets, many of them rocky worlds possibly similar to Earth. The Milky Way is not just a galaxy. It is an ecosystem of staggering complexity, richness, and age. We have been inside it all our lives, and yet we cannot see its full shape directly. We are embedded within the disk, about halfway out from the center, surrounded by the light of the surrounding stars in all directions. The Milky Way we see on a dark night, that faint luminous band arching across the sky, is a cross-section of our own galaxy, seen from inside. We are looking along the disk, where the concentration of stars is highest, and that concentration of light creates the band. For much of human history, the Milky Way was thought to be the entirety of the universe. It was only in 1924 that the American astronomer Edwin Hubble, using the Great 100-inch telescope at Mount Wilson Observatory, demonstrated definitively that the fuzzy, spiral nebulae seen through smaller telescopes were in fact other galaxies. Island universes separate from and comparable to our own, at distances far greater than anything previously imagined. This discovery, sometimes called the Great Debate's Resolution, transformed our understanding of the universe in a single stroke. We went, overnight, from a universe that was the Milky Way to a universe of billions of galaxies. At the very center of the Milky Way, something waits. Sagittarius A star, abbreviated SGRA star, pronounced Sagittarius A star. Sagittarius A star is a supermassive black hole with a mass approximately 4 million times that of our Sun. It sits at the heart of our galaxy like a great, dark eye, invisible itself but betrayed by the orbits of stars wheeling around it at tremendous speeds. The stars that orbit closest to SGRA star, a group called the S stars, move at velocities of thousands of kilometers per second, completing orbits that take only a few years. By tracking these orbits with high-precision infrared telescopes over many years, astronomers were able to infer the presence and mass of SGRAU with extraordinary accuracy. Even before any direct image was obtained, the Nobel Prize in Physics in 2020 was awarded partly for this work to Reinhard Genzel and Andrea Ghez. 2022, a collaboration called the Event Horizon Telescope, a global network of radio observatories working together, effectively creating a radio telescope the size of Earth, released the first direct image of Sagittarius A star. It showed a bright, diffuse ring of superheated gas surrounding a central shadow. The shadow cast by the event horizon against the glowing background of the accretion flow. The image matched the predictions of general relativity with remarkable precision. 4 million solar masses. The Sun, a star powerful enough to sustain all life on Earth, to drive our weather and our seasons to have burned without pause for 5 billion years, has a mass of about 2 × 10⁻³ power kilograms. 4 million times that. This is Sagittarius A star. The event horizon of Sagittarius A star has a radius of roughly 12 million kilometers, about 17 times the radius of the Sun. If you replace the Sun with Sagittarius A star, the event horizon would not even reach the orbit of Mercury, small by the standards of what we are traveling toward. Sagittarius A star is currently relatively quiet, in an astronomically dormant state. It is not actively consuming large amounts of matter. It is not a quasar. Occasionally, it experiences brief flares, when small amounts of gas or stellar debris fall close to the event horizon and release intense bursts of X-ray radiation. But compared to many galactic centers we observe, ours is quiet. Peaceful, even. It may not always have been so. Millions of years ago, perhaps only a few million, which is recent on cosmic timescales, SGR-AQs may have been far more active. There is evidence in the structure of gas and radiation above and below the galactic plane of past energetic events from our galaxy's center. The Fermi bubbles, vast structures extending roughly 25,000 light-years above and below the center of the Milky Way, discovered by NASA's Fermi Gamma Ray Space Telescope in 2010, are thought to be the remnants of a period of much greater activity from SGR-A* in the past. Our own galactic center has a complicated history, and the black holes we are traveling toward make SGR-A* look like the gentlest of introductions. Let us continue outward. Let the Milky Way itself shrink behind us. Let it become what it appears to be from great distance, a glowing spiral smear of light against the dark. A galaxy, one of many. The closest large galaxy to the Milky Way is the Andromeda Galaxy, designated M31 in Messier's catalogue. It is a spiral galaxy similar in many ways to our own, containing perhaps 1 trillion stars, making it somewhat larger than the Milky Way. Andromeda is about 2.537 million light-years from Earth. The light we see when we look at Andromeda left it 2.5 million years ago. We are seeing it as it existed when our early human ancestors were just beginning to walk upright on the African savanna. Homo habilis, one of our earliest known ancestors, was alive when that light began its journey to us. Andromeda is the farthest object visible to the naked eye under dark skies, a faint, elongated smudge of light in the constellation of the same name. It appears about 3 times the diameter of the full moon on the sky, though its outer halo extends much farther still. Ancient peoples saw it. Medieval astronomers catalogued it. Modern astronomers have mapped it with extraordinary care and precision. In approximately 4.5 billion years, the Andromeda Galaxy and the Milky Way are destined to collide. This is not a prediction based on speculation, but on precise measurements of Andromeda's motion using the Hubble Space Telescope and other observatories. The two galaxies are approaching each other at roughly 110 kilometers per second. When they meet, the collision will not be a sharp impact, but a slow, drawn-out gravitational interaction spanning hundreds of millions of years. The spiral structures of both galaxies will be disrupted. Stars will be flung into new orbits. Some may be ejected entirely from the merged system. Eventually, after perhaps 2 or 3 billion years of merging and oscillating, the two galaxies will settle into a single, large, elliptical galaxy. Astronomers have already given this future object a name: Milkomeda, or sometimes Milkdromeda. The name is somewhat whimsical, but the science behind it is precise. Computer simulations of the merger have been run in extraordinary detail, and they paint a remarkable picture of the sky as it will appear in the distant future. Filled with the diffuse glow of the merging galaxies, the star density increasing, the familiar patterns of the Milky Way's spiral arms dissolving into something new. The solar system itself will likely survive this merger. The distances between stars are so large that even in the densest regions of merging galaxies, stellar collisions are extraordinarily rare. Our Sun and its planets will probably persist through the merger event, though their position within the merged galaxy will change dramatically. But Andromeda is just our nearest large neighbor. Beyond it, the universe reveals itself as something far more complex and interconnected than we might initially imagine. The Milky Way and Andromeda, along with the smaller Magellanic Clouds and approximately 80 other dwarf galaxies, form what is called the local group. The local group is a gravitationally bound collection of galaxies spread across a region roughly 10 million light-years in diameter. It is our corner of the universe, our immediate neighborhood. The galaxies of the local group know about each other gravitationally. They interact, orbit around the group's collective center of mass, occasionally collide and merge. But even the local group is just a small part of a larger structure. The local group is one of many galaxy groups and clusters within what is called the Virgo supercluster. This vast, loosely bound congregation of galaxies spans approximately 110 million light-years in diameter and contains roughly 100 galaxy groups and clusters, with a total estimated mass of about 1,000 trillion solar masses. At its center sits the Virgo cluster, a dense concentration of about 1,300 galaxies packed into a region roughly 15 million light-years across, with the giant elliptical galaxy M87 near its center. The Virgo cluster is the dominant gravitational presence in our cosmic neighborhood, and the Milky Way, along with the entire local group, moves gently in its direction, drawn by its immense mass. But even the Virgo supercluster is just one node in a still larger web. In 2014, a team of astronomers led by R. Brent Tully of the University of Hawaii identified an even more enormous cosmic structure, Laniakea. The name means immeasurable heaven in Hawaiian, and it is an appropriate choice. Laniakea is a supercluster of superclusters, a vast cosmic structure containing the Milky Way along with approximately 100,000 other galaxies, spread across a region roughly 500 million light-years in diameter. The total mass of Laniakea is estimated at around 100 million billion times the mass of the Sun. To define Laniakea, the astronomers used a new method. They mapped the motions of thousands of galaxies, tracing how each galaxy was moving through space. By identifying the gravitational basins, the regions within which galaxies are flowing toward a common center, like water flowing into a basin, they could define the boundary of the supercluster. Laniakea is, in this sense, defined by gravity and motion, by the flows of matter through cosmic space. And still, Laniakea is just one structure among many in the observable universe. When astronomers look at the universe at the very largest scales, distances of hundreds of millions to billions of light-years, they see what is known as the cosmic web, a vast, three-dimensional network of filaments and sheets of galaxies, interconnected like threads in an extraordinary tapestry with enormous voids between them. The filaments are threaded with dark matter, the mysterious substance that makes up about 27% of the universe's total energy content, that doesn't interact with light, but exerts gravitational influence. These dark matter filaments channel galaxies and gas along their lengths, funneling them toward massive clusters at the intersections. The voids between the filaments are immense. Some cosmic voids span hundreds of millions of light-years, regions of space so empty that they contain almost no galaxies at all. If our Milky Way were located in the center of a large void, rather than in its current position within the cosmic web, our entire observable universe's night sky would look dramatically different. Far fewer galaxies, a much emptier cosmos. The cosmic web is perhaps the largest coherent structure in the universe, and it is, when visualized by computers using data from large-scale surveys, strikingly beautiful and, strikingly, reminiscent of biological structures. The filaments of the cosmic web look remarkably like the neural networks of a brain, or the threads of a fungal mycelium, or the vascular system of a leaf. This similarity is not coincidental in some deep philosophical sense, though it is not a direct, causal connection. It is a consequence of the mathematics of network formation. Systems that grow by connecting nodes through pathways tend to produce similar topological structures, regardless of the underlying physical mechanism. The observable universe, everything we can, in principle, detect with our telescopes, spans approximately 93 billion light-years in diameter. It contains an estimated 2 trillion galaxies. 2 trillion. Each galaxy containing tens to hundreds of billions of stars. The resulting number of stars in the observable universe is approximately 200 sextillion. A 2 followed by 23 zeros. We cannot truly comprehend these numbers intuitively. We can work with them mathematically. We can write them down. But to feel what 2 trillion galaxies means in the way we feel the distance to a nearby city, that is beyond us. And yet, the attempt to approach these numbers, to stretch the mind toward them, is one of the most distinctly human activities there is. And within this vast, intricate, ancient structure, this universe of trillions of galaxies and hundreds of sextillions of stars, there are objects of almost unimaginable extremity. Objects that represent the universe's capacity for concentration, for gravity, for energy, pressed to the very limits of what the laws of physics allow. We are approaching the realm of the black hole. Let us pause here in the immensity of intergalactic space and take a moment to understand what a black hole truly is. Because the word is so familiar now, so embedded in popular culture, in science fiction and news headlines and casual conversation, that it is easy to forget how genuinely extraordinary, how genuinely strange these objects are. A black hole is a region of space where matter has been compressed into such extreme density that the gravitational force it exerts is strong enough to prevent even light from escaping. The escape velocity, the speed an object would need to attain to break free from the gravitational pull, exceeds the speed of light itself. And since nothing in the universe can travel faster than light, nothing can escape. Not radiation, not particles, not information. This is not a metaphor. This is physics. The idea that sufficiently massive objects might trap even light was suggested as early as the 18th century by the English astronomer John Michell in 1783, who called such objects dark stars. But the modern understanding of black holes emerged from Einstein's general theory of relativity, published in 1915. General relativity fundamentally changed our understanding of gravity. Rather than describing it as a force acting between masses, Einstein described it as a curvature of space-time caused by mass and energy. Objects follow curved paths through space not because a force is pulling them, but because space-time itself is curved, and they are following the straightest possible path through a curved geometry. In regions of extreme mass concentration, this curvature becomes extreme. And at the boundary of a black hole, the event horizon, the curvature becomes so severe that all paths through space-time lead inward. The escape velocity at this boundary is exactly the speed of light. Just inside it, the escape velocity exceeds light speed. And since nothing can travel faster than light, nothing can escape. Karl Schwarzschild, a German physicist, derived the first exact solution to Einstein's field equations that described such a singularity in 1916. From the trenches of World War I, while serving in the German army on the Russian front, he sent the solution to Einstein, who was astonished by its elegance. The Schwarzschild radius. The radius at which any mass compressed sufficiently would form a black hole is the fundamental scale of black hole physics. For the Earth, the Schwarzschild radius is about 9 millimeters. If all the Earth's mass were compressed into a sphere 9 millimeters across, it would become a black hole. For the Sun, it is about 3 kilometers. The event horizon is not a physical surface, it is a mathematical boundary, the point of no return. If you were to fall through it, you would not, in the moment of crossing, feel anything unusual. For a sufficiently large black hole, the tidal forces at the event horizon might be gentle enough that you would pass through without any immediate physical discomfort. But the moment you crossed it, your fate would be sealed. Every path through space-time within the event horizon leads toward the singularity. This is a statement not about force or power, but about the geometry of space-time itself. Moving inward is not something you are compelled to do. It is simply the only direction there is. The singularity, the central point or region of a black hole where the known laws of physics, as we currently understand them, break down. Our equations produce infinite values here, infinite density, infinite space-time curvature. This tells us not that infinities actually exist at the center of a black hole, but that our theories have reached their limit. The singularity is the edge of the map of known physics. Physicists believe that a complete theory of quantum gravity, a framework that successfully unifies general relativity with quantum mechanics, would be needed to fully describe what happens at and within the singularity. These two great pillars of modern physics, general relativity and quantum mechanics, are each extraordinarily successful in their respective domains. But they are mathematically incompatible with each other in extreme regimes. And the singularity of a black hole is the most extreme regime in the universe. The singularity is, in a sense, an invitation to the physics of the future, a place where a better, more complete theory must be found. We do not yet have that theory. String theory, loop quantum gravity, and several other frameworks have been proposed as candidates. Each has mathematical elegance and some promising features. None has yet produced a complete, fully verified description of the physics at the singularity. The mystery remains open. Black holes form in several ways. The most familiar is the death of a massive star. When a star with a mass greater than about 8 times the Sun exhausts its nuclear fuel, its core collapses in a fraction of a second to extraordinary density. If the remaining core mass is large enough, greater than about 2 or 3 solar masses, neutron degeneracy pressure cannot halt the collapse, and a black hole forms. The surrounding stellar envelope is explosively ejected in a supernova, briefly outshining an entire galaxy. The black hole left behind, a stellar mass black hole, has a mass of perhaps 10 to 100 times the Sun. But stellar mass black holes are small change, cosmically speaking. Supermassive black holes, found at the centers of most large galaxies, are a different order entirely. They contain millions to billions of solar masses, and they are present in virtually every galaxy above a certain mass threshold. Our own Milky Way has one, Sagittarius, a star, at 4 million solar masses. The Virgo A galaxy, M87, has one, M87 star, at approximately 6.5 billion solar masses. The black hole, whose image was first captured by the Event Horizon Telescope in 2019, the first direct image of a black hole ever obtained. And then there are the ultra-massive black holes, the category that represents the universe at its most extreme. Black holes whose masses are measured not in millions, but in tens of billions of solar masses. Objects so large that the very concept of large requires revision. We are traveling toward the largest of these. In the constellation Canes Venatici, the hunting dogs, a modest constellation in the northern sky between Boötes and Ursa Major, there is something that defies all ordinary description of size. It lies at a distance of approximately 10.4 billion light-years from Earth. The light we observe from it today left its source when the universe was only about 3.4 billion years old, barely a quarter of its current age. The universe was younger then, hotter, denser, more turbulent. Galaxies were still assembling from the primordial gas. Stars were forming at rates far higher than today. The cosmic web was taking shape. It was a different epoch, the cosmic dawn of the great structures we see around us. And in this young, violent, luminous early universe, one object was already extraordinary. TON 618. The name comes from the Tonantzintla catalogue, a survey of blue stellar objects conducted in the 1970s at the Tonantzintla Observatory in the state of Puebla, Mexico. The observatory sits at over 2,000 meters elevation, its telescope aimed at the southern Milky Way and the surrounding sky, cataloguing stars and quasi-stellar objects. When the survey team first identified the source that would become TON 618, it appeared as a faint blue point of light. Spectroscopically unusual, its light slightly red-shifted in a way that suggested it was either unusual or very distant. It was very distant. To understand what TON 618 is, we first need to understand what a quasar is. A quasar, short for quasi-stellar radio source, is the active nucleus of a distant galaxy, powered by a supermassive or ultramassive black hole that is actively consuming enormous quantities of material. As gas, dust, and stellar matter fall toward the black hole, they form an accretion disk, a vast, swirling structure of superheated plasma. As this material spirals inward, losing energy through friction and magnetic interactions, it converts gravitational potential energy into heat and radiation with extraordinary efficiency. The inner regions of the accretion disk reach temperatures of tens of millions of degrees and emit radiation across the entire electromagnetic spectrum. Quasars are among the most luminous objects in the universe. The most powerful quasars can outshine entire galaxies, more than 100 billion stars, from a region smaller than the solar system. They can be seen from across billions of light years. They're brilliant light beacons in the deep cosmos. They were most numerous in the early universe, during the so-called quasar epoch, when conditions were ripe for the rapid growth of supermassive black holes and the torrential accretion that feeds quasar activity. TON 618 is one of the most luminous quasars ever discovered. Its bolometric luminosity, the total energy output across all wavelengths, is estimated at approximately 4 × 10 to the 40th power watts. That is about 140 trillion times the luminosity of the Sun. 140 trillion. If you replace the Sun with TON 618, it would not just light our solar system, it would light up a region of space hundreds of light years across with brilliant intensity. But the luminosity of TON 618's quasar phase, extraordinary as it is not the most remarkable thing about it. The most remarkable thing is the mass of the black hole that powers it. Using a technique called reverberation mapping, which measures the time delay between variations in the quasar's central brightness and the corresponding variations in the emission from the surrounding broadline region, a region of gas orbiting the black hole at distances of light weeks to light months. Astronomers were able to estimate the mass of TON 618's central black hole. The result is staggering. TON 618 contains a black hole with a mass of approximately 66 billion times the mass of the Sun. 66 billion solar masses. Let us try to understand what that means. The Sun has a mass of approximately 2 × 10 to the 30th power kilograms, 2 followed by 30 zeros. It contains 99.86% of all the mass in the solar system. It has been burning nuclear fuel for 4.6 billion years and will continue to do so for another 5 billion years. It is, by the standards of daily life, immense. TON 618's black hole has a mass 66 billion times greater. If you tried to count the number of solar masses in TON 618's black hole at a rate of 1 per second, one solar mass, tick, one solar mass, tick, it would take you more than 2,000 years to finish counting. You would need to start in the age of the Roman Republic and count continuously, without pause, to the present day. Sagittarius, a star, the black hole at the center of the Milky Way, which contains 4 million solar masses, is itself an object of extraordinary mass. And yet, TON 618 is approximately 16,500 times more massive than Sagittarius A star. If Sagittarius A star is a large mountain, TON 618 is a continent. If Sagittarius, a star, is the entire ocean, TON 618 is the entire planet. The event horizon of TON 618, the spherical boundary within which nothing can escape, has a radius of approximately 1,300 astronomical units. 1 astronomical unit is the average distance from the Earth to the Sun, 150 million kilometers. The radius of TON 618's event horizon is 1,300 times this distance. Let us trace that distance in the solar system. Start at the Sun. Travel past Mercury, past Venus, past Earth, past Mars, past the asteroid belt, past Jupiter, past Saturn, past Uranus, past Neptune. You are now 30 astronomical units from the Sun at the orbit of Neptune, the outermost planet. Keep traveling, past 100 astronomical units, deep in the Kuiper belt, past 200 astronomical units, past 500 astronomical units, past 1,000 astronomical units. At 1,300 astronomical units, you would be at the event horizon of TON 618. If the black hole were centered on the Sun, the entire solar system from the Sun to the edge of the Kuiper belt, everything that most people consider the solar system, fits within the event horizon of TON 618 with room to spare. In fact, the event horizon extends 4 times farther from the center than the orbit of Neptune. The entire planetary system of our Sun, all of the planets, all of the moons, all of the asteroids, all of the comets we know, could fit inside the event horizon of TON 618. Inside it, contained within it, surrounded by the absolute blackness of the event horizon on all sides. This is not poetic exaggeration. This is straightforward geometry. Now consider the following. The event horizon of Sagittarius, a star, has a radius of about 12 million kilometers, roughly 0.08 astronomical units. The event horizon of TON 618 has a radius of 1,300 astronomical units. This means TON 618's event horizon is approximately 16,000 times larger in radius than Sagittarius A's. And since the volume of a sphere scales as the cube of the radius, TON 618's event horizon encloses a volume roughly 4 trillion times larger than that of Sagittarius A's, 4 trillion times larger in volume. These numbers are not meant to overwhelm. They are meant to illuminate. They tell us something about the extraordinary range of scales that the universe operates across, from the smallest subatomic particles to the largest gravitational objects, and about the power of gravity, given enough mass and time to create structures of almost inconceivable magnitude. TON 618 is the largest black hole we know. It sits at the extreme end of the distribution of all known black hole masses. It is, in a very real sense, the universe's answer to the question, how extreme can a gravitational object get? We are about to find out what it looks like. Let us make the final approach. We have traveled billions of light years. We have left the Earth behind. left the solar system behind, left the Milky Way behind. We have moved through the local group, through the Virgo supercluster, through Laniakea, through the vast threads of the cosmic web. We have seen the universe at its largest scales, the filaments and voids, the galaxy clusters and superclusters, the architecture of matter stretching across billions of light years. And now, ahead of us, the host galaxy of TON 618 begins to resolve from the background of distant lights. It is a large, luminous elliptical galaxy. Elliptical galaxies, designated by the letter E, followed by a number indicating their degree of elongation, are among the most massive galaxies in the universe. Unlike the elegant spiral galaxies with their star-forming arms and disk structure, elliptical galaxies are more diffuse, rounded, and dominated by older stellar populations. They have largely exhausted their cold gas supply, so new star formation is rare. Their light is dominated by the warm glow of old, red, and orange stars, the remnants of billions of years of stellar evolution. The host galaxy of TON 618 glows softly, a luminous oval suspended in the dark, surrounded by the faint halos of globular clusters, the distant shimmer of satellite galaxies, the complex architecture of a massive galactic system that has been assembling over billions of years. But at its center, even at this distance, there is something different. A brightness that does not belong to the ordinary light of stars. A luminosity that seems almost violent in its intensity, even seen from far away. That is the quasar. That is TON 618, blazing in its youth, as it appeared 10.4 billion years ago when the light we are now observing first began its journey. As we move closer, the quasar's light begins to dominate everything around it. It is outshining the entire host galaxy, outshining the light of hundreds of billions of stars, all from a region smaller than the solar system. This is the fundamental paradox of quasars. They are powered by an object that emits nothing, yet they are among the brightest things in the universe. The energy comes not from the black hole itself, but from the process of matter falling into it. As material spirals inward through the accretion disk, gravitational potential energy is converted into heat and radiation with remarkable efficiency. Quasar accretion can convert matter to energy with an efficiency of 10 to 40%, depending on the black hole's spin. Compare this to nuclear fusion, the process that powers stars, which converts only about 0.7% of the hydrogen fuel's mass into energy. Quasar accretion is, mass for mass, far more efficient than the process that powers the Sun. Now we are in the galaxy's outer halo, moving inward through the dim outer reaches of stellar populations. The light of the galaxy's billions of stars washes over us, ancient and patient. We can see the galaxy's structure, the smooth, featureless gradient of stellar density increasing toward the center. The occasional satellite galaxy caught in gravitational interaction, the faint streams of stars that mark ancient mergers long since completed. The center is bright, uncomfortably bright, even from this distance. We continue inward, and then the accretion disk comes into view. It is not what you might expect. There is no simple, clean ring of fire. The accretion disk of an active quasar is a vast, swirling, turbulent structure. Superheated plasma threading through powerful magnetic fields, convecting, compressing, radiating. The inner accretion disk reaches temperatures of tens of millions to hundreds of millions of degrees. At these temperatures, matter does not simply glow. It blasts out X-rays and ultraviolet radiation in quantities that would sterilize everything within light years, were there anything to sterilize. At the very heart of the accretion structure, the innermost stable circular orbit, the closest orbit at which matter can stably circle the black hole before inevitably falling inward, the luminosity is greatest. This inner edge is where the disk terminates and the plunge region begins. Material crossing. This boundary is committed. It has passed the point where the gravitational gradient allows stable orbits. It will fall inward, releasing its remaining energy in a final burst of radiation, and then pass the event horizon into silence. From a safe distance, the visual effect is extraordinary. The black hole at the center, though it itself emits nothing, is surrounded by the blazing accretion disk. The gravity of the black hole is so intense that light passing near the event horizon is bent dramatically. Light from the far side of the accretion disk, the portion that would be hidden behind the black hole, is bent completely around the black hole and reaches us from in front of it, creating a bright ring, a photon ring, that traces the gravitational lensing of the background light. This photon ring is the bright, circular feature seen in Event Horizon Telescope images of black holes. The glowing ring that surrounds the central shadow. And at the center of that ring, the shadow. The absolute, perfect darkness of the event horizon. Not literally a shadow in the photographic sense, but a region where no photons can escape to reach us, surrounded by the brilliance of trapped and bent light. It is, in the most literal sense, a hole in the fabric of observable reality, a place where our ability to receive information ends. The event horizon of TON 618, seen up close, spans more than 2,600 astronomical units across, larger than the solar system. The shadow cast by it against the background of the accretion disk and the relativistically lensed galaxy light behind it would be vast. Not a point, not a small disk. A great, dark sphere of absence surrounded by the most energetic environment in the visible universe. The silence here, and we must use the word silence in its full metaphorical weight, knowing that space is always silent, is of a different kind. It is not the silence of empty space, which is simply the absence of a medium for sound. It is the silence of a boundary, of a threshold, of the place where all information ends. The event horizon says nothing. It gives nothing back. It has consumed over billions of years, quantities of matter equivalent to 66 billion suns. And it has given nothing to indicate what became of that matter, except for the gravity that its mass generates. The stars behind us appear distorted. Light from distant stars and galaxies, passing near the event horizon on its way to us, is bent by the extreme curvature of space-time. Some stars appear in multiple positions simultaneously, their light reaching us by different paths around the black hole. The sky becomes a visual symphony of distortions, a gravitational kaleidoscope. The familiar linear progression of light rays through space ceases to apply. Here, space itself is the lens, and closer still, time begins to behave differently. Gravitational time dilation, the slowing of time near a massive gravitational source, is one of the most thoroughly tested predictions of general relativity. It has been measured in GPS satellites, which must account for time dilation to maintain accurate positioning. It has been measured in laboratory experiments with atomic clocks at different altitudes. It is not a theoretical nicety. It is a measured fact of how time behaves in gravitational fields. Near the event horizon of TON 618, time runs at a dramatically slower rate than it does far from the black hole. For an observer hovering just outside the event horizon, an impossibly energy-demanding feat, the rest of the universe would appear to fast forward. Stars would be born and die. Galaxies would evolve. the cosmic web would continue its slow growth. All of it compressed from that hovering observer's perspective into a much shorter experience of time. And at the event horizon itself, time dilation becomes infinite. From the perspective of a distant observer, someone falling into the black hole appears to slow down, redshift, and freeze, eventually fading from view as the light from them becomes infinitely redshifted. They never, from the distant observer's perspective, actually cross the event horizon. They appear to hang there, frozen, redshifting into invisibility. But from the perspective of the falling observer, they cross the event horizon in finite time. They do not freeze, they continue to fall. And once they have crossed, they are in a region of space-time from which no information can return. Two perspectives, both valid, both described by the same mathematical framework of general relativity. Both, in their own way, deeply strange. The black hole does not care about any of this. It does not care about our wonder or our equations or the centuries of human science and philosophy that brought us to the point of understanding it. It exists in exactly the way it has existed for billions of years. Patient, absolute, ancient. It will continue to exist for far longer. There is a thought experiment that physicists and science communicators return to often because it illuminates the nature of black holes in ways that pure mathematics cannot fully capture. The thought experiment is this: what would actually happen to you? A human being, a body of approximately 70 kilograms of water and carbon and calcium. If you approached and then fell into a black hole? The answer depends profoundly on the size of the black hole. And this is where TON 618's immensity becomes, in a strange and counterintuitive way, almost forgiving. For a stellar mass black hole, one with a mass of, say, 10 times the Sun, the event horizon is tiny, only about 30 kilometers in radius. At this scale, the difference in gravitational pull between the near side of your body and the far side, even at the distance of the event horizon, is enormous. The gravitational gradient, the rate at which the gravitational field strengthens as you approach, is very steep for small black holes. And it is this gradient, this tidal force, that does the damage. Tidal forces arise whenever gravity acts differently on different parts of an extended object. The Moon exerts tidal forces on the Earth. The near side of the Earth is pulled slightly more strongly than the far side, creating the tidal bulges in the oceans. But the Earth is large, and the gradient of the Moon's gravity across it is gentle. For a human approaching a stellar mass black hole, the gradient is anything but gentle. The process has been given a wonderfully descriptive name: spaghettification. The near side of your body, the side facing the black hole, is pulled more strongly than the far side. This difference creates a net stretching force along the radial direction, elongating you. Simultaneously, forces from the sides compress you inward. The net result is that you are stretched into a long, thin strand, spaghettified by the extreme tidal gradient of the gravitational field. For a stellar mass, black hole spaghettification would occur well before you reach the event horizon. You would be pulled apart lethally and completely, while still thousands of kilometers from the boundary. But TON 618 is different. TON 618 is so immensely massive that its event horizon is so large that the gravitational gradient across a human body at the event horizon is far gentler. The tidal forces at the event horizon of TON 618 are, by the most straightforward calculations, quite small. Smaller, in fact, than the tidal forces you experience standing on the surface of the Earth from the Moon's influence. Negligible. Harmless. This means that, in principle, a human being could fall through the event horizon of TON 618 without experiencing any physical distress in that moment. No alarm bells, no sudden pain, no physical sensation of crossing a threshold. The accretion disk, of course, would be a lethal environment long before you reach the event horizon. The radiation, the superheated plasma, the extreme particle energies would be fatal long before any gravitational effects became noticeable. But setting aside the practical details of survival, the physics of the event horizon crossing itself is, for TON 618, surprisingly undramatic, which makes the reality of what you have just done all the more profound. You have passed through the event horizon of the largest known black hole in the observable universe, and in the moment of doing so, nothing unusual happened. No warning, no notification, and yet, from that moment, you are in a region of space-time from which there is no return. What would you see? From just inside the event horizon, looking outward, you would see the entire outside universe, but compressed into a shrinking window of view. As you fell further inward, the window of visible universe would shrink, the light from outside becoming increasingly blue-shifted, increasingly intense. Eventually, the entire observable universe would appear compressed into a small, bright circle directly ahead, in the direction away from the singularity, and behind you, only darkness. The experience of time would continue normally from your perspective. Your own clock would tick at its usual rate. The processes of your body would continue at least for a while. You would have time, perhaps hours, given the immense size of TON 618's interior, before tidal forces became significant. Time to observe, time to think, time to experience the interior of the most extraordinary object in the known universe. Eventually, as you drew closer to the singularity, tidal forces would increase. The gravitational gradient, gentle at the event horizon, becomes steeper as you approach the center. Spaghettification would, at some point, become unavoidable. Our physics cannot tell us exactly what you would experience in the final moments, because the singularity is a region where our current theories cease to apply. Perhaps the singularity is not a point at all, but a region described by quantum gravitational effects that soften the infinite densities our classical equations predict. Perhaps the interior of a black hole is connected through space-time geometry to other regions of the universe, a possibility suggested by certain theoretical solutions called Einstein-Rosen bridges, or wormholes. Perhaps the singularity is the boundary of something entirely new, something that no current human theory has yet imagined. These are not idle speculations. They are the leading edge of physics research. The interior of a black hole is one of the places where the next great theory of nature will have to apply, where a unified framework of quantum mechanics and gravity will make predictions that differ from our current understanding, and where those predictions will need, somehow, to be tested. There is also the question of information. In quantum mechanics, information is preserved. The evolution of quantum systems is governed by equations that are time-reversible. In principle, if you knew the exact state of a system at any moment, you could calculate both its past and future. Information is never truly destroyed, but what happens to information that falls into a black hole? From the outside, it appears to vanish. The black hole responds to infalling matter only through its mass, charge, and spin. Nothing else. All other information about the infalling material, its composition, its structure, its quantum state, seems to be lost. This is known as the black hole information paradox, and it has been one of the central unresolved questions in theoretical physics for decades. Stephen Hawking suggested in 1974 that black holes are not entirely black, that quantum effects near the event horizon cause a slow, steady emission of thermal radiation, now called Hawking radiation. This radiation arises from quantum fluctuations near the event horizon, and it carries away energy from the black hole, gradually causing it to evaporate over extraordinarily long timescales. For Torn 618, the Hawking evaporation timescale is beyond astronomical. It would take a number of years with roughly 100 digits to express before Torn 618 would evaporate by this process, and that is far, far longer than the current age of the universe. But the theoretical significance of Hawking radiation is enormous. It suggests that information is not permanently lost, that it is encoded somehow in the radiation emitted during evaporation. The precise mechanism by which information escapes from a black hole remains a subject of intense research and debate. It is one of the frontiers of theoretical physics. The black hole, in other words, is not merely a curiosity. It is a test of our deepest understanding of nature. It sits at the intersection of general relativity and quantum mechanics, the two great and mutually incompatible theories of modern physics. And its existence demands that we find a way to reconcile them. TON 618, the largest and most massive, represents this challenge at its most extreme. We are a long way from home. From here, wherever here is, in the vast intergalactic space near the region of sky where TON 618 resides. The Milky Way is invisible to the naked eye. It is lost among billions of other faint galaxies. Our solar system, our Earth, every human being who has ever lived and loved and dreamed, all of it is hidden in the undifferentiated light of a galaxy too small and distant to distinguish from the countless others scattered across this dark. And yet, something extraordinary has happened. We have been here in imagination. We have made this journey not physically, but cognitively and emotionally, using the tools of mathematics and observation and language that our species has developed over thousands of years. We have stretched our minds across 10.4 billion light-years. We have tried to hold in some small way something that exists at the absolute extreme of what the universe is capable of producing. This is, when you sit with it, one of the most remarkable things about being human. We are small, we are fragile. We live on a thin film of atmosphere wrapped around a rock, orbiting an unremarkable star in the outer suburbs of one galaxy among 2 trillion. Our lives are brief by cosmic standards. The entire span of recorded human history, from the first written records of ancient Sumeria to the current moment, is less than a single flash of cosmic time. Against the backdrop of the universe's 13.8 billion year history, all of human civilization occupies a fraction of the last second of a year-long reel. And yet, from this tiny, fragile vantage point, we have mapped the universe. We have measured it. We have discovered TON 618. We have calculated the mass of its black hole, the radius of its event horizon, the luminosity of its quasar, the distance to its host galaxy, all without ever leaving our own planet. With telescopes and radio arrays and the mathematics of general relativity, we have reached across 10.4 billion light-years and weighed something. This is not insignificance. This is the opposite of insignificance. This is what it looks like when consciousness meets the universe honestly, without flinching, without retreating into comfortable smallness, but reaching outward with every tool at its disposal. Carl Sagan wrote that we are a way for the cosmos to know itself. It is a beautiful thought, and it has always seemed true in some deep sense. The atoms in our bodies were forged in the hearts of stars. The carbon in our cells was created through stellar nucleosynthesis. in the cores of stars that lived and died before the sun was born. The iron in our blood was scattered across space in the explosions of supernovae, scattered as dust into the interstellar medium, gathered into the nebula that became our solar system, condensed into the Earth, dissolved into the oceans, incorporated into the chemistry of life. We are, in the most literal chemical and physical sense, made of stars. And now, we are looking at one of those stars' most extreme descendants, a black hole 66 billion times the mass of the Sun. And we are thinking about it. A universe that made stars has, through billions of years of complexity and evolution, produced beings who can study the remnants of those stars. The universe, through us, is examining itself. There is a particular kind of wonder that comes not from the exotic and unfamiliar, but from the recognition of kinship. When we study TON 618, we are not looking at something alien, something wholly other. We are looking at a part of the same universe that made us. The same physical laws that govern the electrons in the neurons of your brain as you process these words govern the flow of plasma in the accretion disk of TON 618. The same mathematics describes both. The same fundamental constants, the speed of light, the gravitational constant, Planck's constant, operate everywhere we have ever looked. This universality of physical law is one of the most profound things science has discovered. It means that the universe is coherent, that it plays by the same rules everywhere, from the smallest scale to the largest, from a quantum foam of virtual particles to the event horizon of the largest black hole in the observable universe. One set of rules, one universe. We do not fully understand all of those rules. There are deep and genuine mysteries remaining. We do not know what dark matter is. We do not know what dark energy is. We do not have a complete theory of quantum gravity. We do not know whether the observable universe is all there is, or whether it is one small region of a much larger, perhaps infinite, cosmos. We do not know whether life and consciousness are rare or common, whether we are the universe's only instance of self-awareness or one among billions. These mysteries are not failures. They are invitations. They are the reason that people choose to spend their lives doing science. The reason telescopes are built, satellites are launched, equations are written, data is analyzed. The mystery is not the obstacle. The mystery is the point. TON 618 embodies this better than almost anything else. We have measured it to remarkable precision. We know its mass, its distance, its luminosity, and yet we cannot fully explain how it formed, how any black hole grows to 66 billion solar masses in the time available in the early universe. We cannot describe what happens at its singularity. We cannot know what the universe looks like from inside its event horizon. We cannot fully account for what happens to the information that has fallen into it. It is known and unknown, measured and mysterious, all at once, as is the universe. Now let us begin the long journey home. Imagine the reverse of our path. TON 618 host galaxy receding, shrinking to a point of light. The cosmic web drawing back its vast filaments, becoming faint threads, then invisible. The Virgo supercluster appearing ahead of us, a concentrated glow against the cosmic background. Laniakia's structure resolving as we approach it. The Milky Way growing, a faint smear, then a disk, then a spiral, then the familiar band of light that arches across our night sky. The solar system appearing, the sun brightening, the Earth resolving from a point to a disk to a world, and then home. The blue oceans, the white clouds, the thinner line of the atmosphere, the the quiet green and brown of continents, the familiar planet turning slowly in its orbit, bathed in the light of an ordinary yellow star. This is where we live. This is the single world among all the billions of worlds in the observable universe, where life as we know it has arisen, where consciousness has evolved, where the question, "What is out there?" was first asked. It is a small world. It is a fragile world. It requires care. The same curiosity that takes us on journeys to the edges of the observable universe must also turn its attention to the place we call home, to the thin shell of atmosphere, the complex web of ecosystems, the extraordinary chemistry of life that makes this planet unlike any we have yet found. The universe is indifferent to whether the Earth persists or perishes. Its physical laws make no provisions for the well-being of small, blue, life-bearing planets. That is not the universe's department. It is ours. The awareness of our smallness and fragility in the cosmos is not a reason for despair. It is a reason for tenderness, for the kind of care that arises not from fear, but from understanding. We know how rare this is. We know what the universe looks like at its most typical: vast, cold, empty, dark. Most of it contains nothing living. Most of it has never known warmth in the biological sense. And yet here, around this unremarkable star, in this ordinary galaxy, on this small blue world, here somehow, life arose. Consciousness arose. Language arose. And with language, the ability to make this journey together in imagination across 10.4 billion light years. Sit quietly for a moment with that, not with awe exactly, though awe is appropriate, but with something quieter, something like gratitude, though the universe does not expect or require gratitude, something like wonder that has passed through awe into a more settled, more habitual appreciation of the extraordinary fact of existence. You are here. You exist. You are conscious of existing. In a universe of 93 billion light-years in diameter containing 2 trillion galaxies, you are a small and temporary arrangement of atoms that has become aware of itself and of its context. You have looked out at the universe from inside it, and you have seen what is there. That is extraordinary. That deserves to rest in you for a while. The universe is large. We are small. And somehow, beautifully, we know it. The stars are waiting. There are more journeys to take, more scales to traverse, more mysteries to sit with quietly. The cosmos is patient. It has been here for 13.8 billion years. It will be here for far longer, and we will keep looking outward as long as we are here. Thank you for traveling with Infinite Science. If this journey moved something in you, if the quiet wonder of the universe is something you want to carry with you, we invite you to stay with us. Every video is another journey. Every journey is another attempt to see clearly, to understand honestly, to feel the scale and beauty of the cosmos that contains us. The universe has no edges that we have found. We have not run out of things to discover, and neither have you. The discovery and measurement of TON 618 represents one of the more remarkable achievements of modern observational astronomy. Understanding how scientists arrived at the figure of 66 billion solar masses and why that measurement is trustworthy requires a brief exploration of the techniques involved. Reverberation mapping, the primary technique used to measure the mass of TON 618's black hole, works as follows. Quasars are not perfectly steady light sources. They flicker, varying in brightness over timescales of days to months, driven by instabilities in the accretion disk and fluctuations in the rate of infalling material. The central source of brightness, the innermost accretion disk, varies rapidly. The surrounding gas in the broadline region, which is illuminated by the central source, responds to these variations with a time delay. This delay is the light travel time from the central source to the broadline region. By measuring this delay, astronomers can infer the physical size of the broadline region. The broadline region's size, combined with the velocity of the gas within it, measured from the Doppler broadening of emission lines in the spectrum, allows astronomers to apply the virial theorem to estimate the mass of the central black hole. The virial theorem relates the kinetic energy of the orbiting gas to the gravitational potential of the black hole. It is the same principle that allows us to measure the mass of the Milky Way from the orbital velocities of stars, or the mass of a galaxy cluster from the velocities of its member galaxies. For TON 618, the reverberation mapping was performed using data from multiple observatories over extended monitoring periods. The resulting mass estimate of 66 billion solar masses carries uncertainties. The techniques involve assumptions about the geometry of the broadline region and the dynamics of the gas. But the result has been independently supported by other methods, including estimates based on the quasar's luminosity and accretion physics. The question of how TON 618 formed is one of the most active and challenging areas of research in modern cosmology. The problem is essentially one of time. We observe TON 618's quasar at a redshift corresponding to a look-back time of 10.4 billion years, meaning this is the universe as it existed only about 3.4 billion years after the Big Bang. In that time, a black hole grew to 66 billion solar masses. How? The growth of a black hole requires material to accrete onto it. The Eddington luminosity, the theoretical maximum at which a black hole can radiate while still allowing accretion to continue, sets a limit on the accretion rate. Accretion beyond the Eddington rate would generate so much radiation pressure that the infalling material is blown away. This suggests a maximum growth rate for black holes, and when you calculate how quickly a black hole can grow under Eddington-limited accretion from a seed black hole, the timescales become challenging for objects as massive as TON 618. Several scenarios have been proposed. The initial seed black holes may have been unusually massive. Direct collapse black holes, formed not from stellar remnants but from the collapse of large, primordial gas clouds of tens to hundreds of thousands of solar masses, which then grew rapidly in the dense, gas-rich environments of early galaxies. Or there may have been extended periods of super-Eddington accretion, where the accretion rate temporarily exceeded the nominal limit through complex accretion disk physics. Or the growth may have involved multiple mergers, the black hole at the center of TON 618's galaxy, merging repeatedly with other massive black holes as galaxies merged. Most likely, some combination of these factors contributed. The formation of ultramassive black holes in the early universe remains an open and active research question. The current state of TON 618 is largely unknown because we observe it only as it was 10.4 billion years ago. In the intervening billions of years, its quasar phase has almost certainly ended. Quasar activity requires a plentiful supply of cold gas to feed the accretion disk, and over cosmic time, many galaxy centers have exhausted this supply or expelled it through the energy output of the quasar itself. A phenomenon called AGN feedback, where the energy released by quasar activity heats or blows away the surrounding gas, suppressing both further accretion and star formation. TON 618 today, as it actually exists in the present moment, which we have no means of observing, is almost certainly quiet. A dormant black hole sitting at the center of an evolved elliptical galaxy, its accretion disk dimmed or extinguished, its violent youth far behind it. The black hole itself, of course, persists. Black holes, once formed, can only shrink through Hawking radiation, the incredibly slow quantum mechanical process that causes black holes to emit thermal radiation and gradually lose mass. For a black hole as massive as TORN 618, the evaporation timescale is incomprehensibly long. Using the standard formula for Hawking evaporation, a black hole of TORN 618's mass would require approximately 2 × 10 to the 100th power years to evaporate completely. A number so much larger than the current age of the universe that comparing them is almost meaningless. In the universe's current epoch, the cosmic microwave background radiation has a temperature that far exceeds the Hawking temperature of TON 618, meaning the black hole is actually absorbing more energy from the background radiation than it loses through Hawking radiation. It is, if anything, very slowly growing. TON 618 will outlast everything we know. It will outlast the Sun. It will outlast the Milky Way. It will outlast the era of star formation, which is expected to end within a few trillion years as galaxies exhaust their gas supplies. It will outlast the epoch of stellar remnants. In the unimaginably distant future of the cosmos, long after the last stars have burned out, long after black holes have consumed the remnants of galaxies, long after the universe has cooled and expanded to near absolute zero temperatures, TON 618 will still persist, slowly evaporating, a monument in the dark to the universe's capacity for the extreme. Other ultra-massive black holes have been discovered that rival TON 618. Holm 15A, a galaxy in the Abell 85 cluster, harbors a black hole with a mass of approximately 40 billion solar masses, somewhat smaller than TON 618, but still in the same extraordinary category. The galaxy NGC 4889 in the Coma cluster contains a black hole estimated at roughly 21 billion solar masses. The galaxy NGC 1600 harbors a black hole of about 17 billion solar masses. The universe's most extreme objects come in a range, and TON 618 at 66 billion solar masses currently sits at the top. Whether there are larger black holes in galaxies beyond the reach of our current telescopes or too distant to have been observed yet remains unknown. The observable universe is, after all, only a portion of what exists. Beyond the cosmic horizon, the boundary beyond which light has not had time to reach us since the Big Bang, the universe almost certainly continues. And in that vast, unobservable expanse, there may be black holes larger than TON 618. We cannot know. We can only describe what we can see. What we can see is extraordinary enough. The James Webb Space Telescope, launched in December 2021 and now in full scientific operation, is extending our observational reach into the early universe in ways that are already reshaping our understanding of the formation of the first galaxies and black holes. JWST can detect the light of some of the earliest galaxies ever formed, objects seen as they existed within a few 100 million years of the Big Bang. Among the objects it is studying are early universe black holes and quasars, seeking to understand the conditions under which objects like TON 618 first began to form. Already, JWST has found surprises. Massive galaxies and massive black holes appearing earlier in cosmic history than standard models predicted, suggesting that either our understanding of the early universe needs revision, or that some physical processes operate more efficiently in the early universe than we realized. Science, at the frontier, is always full of surprises. The universe, it seems, has not finished astonishing us, nor are we finished being astonished. Standing at the edge of what we know about the cosmos, it is worth pausing to appreciate the extraordinary chain of understanding that brought us here. It began with curiosity, raw, unmediated curiosity about the lights in the sky. The same curiosity that prompted ancient astronomers in Babylon and Egypt and China and Greece to track the movements of the planets and stars, to notice patterns, to make predictions. The same curiosity that drove Copernicus and Galileo and Kepler to challenge the inherited cosmology of their time. The same curiosity that animated Newton as he formulated his law of universal gravitation. The same law, it turned out, that governed the fall of an apple and the orbit of the moon and the motion of the planets around the sun. All of it, one law, everywhere. Einstein extended this understanding in ways that are still, more than a century later, astonishing in their scope and precision. His general theory of relativity, conceived through thought experiments about the nature of gravity and space-time, refined through mathematics of extraordinary elegance, predicted the bending of light by gravity, the slowing of time in gravitational fields, the existence of black holes, the expansion of the universe, and gravitational waves. All of these predictions have been confirmed experimentally, often with extraordinary precision. None of them were required to be true. The universe simply, extraordinarily, turned out to work the way Einstein imagined it might. The confirmation of gravitational waves in 2015 by the LIGO collaboration was perhaps the most dramatic recent addition to this chain. LIGO, the Laser Interferometer Gravitational Wave Observatory, detected ripples in space-time produced by the merger of two black holes approximately 1.3 billion light-years away. The merger lasted less than a second. The two black holes, each approximately 30 solar masses, spiraled toward each other in the final moments, emitting gravitational waves of increasing frequency and amplitude, and then merged in a brief burst of signal whose shape matched the predictions of general relativity with extraordinary precision. In that moment, instruments capable of measuring a displacement 1,000th the diameter of a proton detected space-time itself vibrating. Black holes had finally spoken to us directly. Since then, LIGO and its partner observatories, Virgo in Italy and Kagra in Japan, have detected dozens of gravitational wave events, black hole mergers, neutron-star mergers, and combinations thereof. Each event is a new data point in our understanding of how black holes form and merge, how massive they can be, and how they populate the universe. For ultramassive black holes like TON 618, direct gravitational wave detection is currently beyond reach. The gravitational waves from the mergers of billion solar mass black holes would have frequencies far too low for ground-based detectors like LIGO. But a future space-based observatory, the Laser Interferometer Space Antenna, or LISA, proposed for launch in the 2030s, will be sensitive to precisely these lower frequencies. LISA may one day detect the gravitational wave signatures of merging supermassive and ultramassive black holes, opening a new observational window onto the most massive gravitational events in the universe. There is also pulsar timing arrays, collaborations of astronomers using precisely timed radio pulsars as natural gravitational wave detectors. By monitoring the precise arrival times of radio pulses from millisecond pulsars scattered across the galaxy, these arrays can detect the subtle perturbations in the timing caused by passing gravitational waves of very low frequency. In 2023, multiple pulsar timing array collaborations around the world announced evidence of a stochastic gravitational wave background, a low-frequency hum of gravitational waves permeating the cosmos, believed to arise from the mergers of supermassive black holes throughout the universe's history. This background is the gravitational echo of billions of black hole mergers, including perhaps the ancestors of objects like TON 618, ringing across cosmic time. The universe is speaking to us in gravitational waves now. We are, slowly and carefully, learning to listen. The story of black hole astronomy is still being written. The instruments are improving. The questions are multiplying. The understanding is deepening. The James Webb Space Telescope is pushing the observational frontier of the early universe ever further back. Future telescopes, ground-based and space-based, optical and radio and gravitational, will extend our reach and sharpen our view. Objects like TON 618 are not curiosities at the edge of knowledge. They are laboratories where the most extreme physics in the universe plays out, and understanding them will teach us things about gravity, space-time, quantum mechanics, and the early universe that we cannot learn any other way. There is no greater adventure, and it is not finished. Not by a long way. In the depths of the universe, across distances measured in billions of light years, ancient light is still traveling toward us. It has been traveling since before the Earth existed. It carries information about the universe in its earliest, most active, most turbulent epoch. The era of quasars and rapid galaxy growth and the formation of the first large structures. When it arrives at our telescopes, we transform it into data, into images, into understanding. We are reading the light of creation. And the universe, patient and enormous and ancient, continues to send its messages across the void. We are still learning to read them. The universe does not owe us wonder. It does not arrange itself for our appreciation. It does not light up its galaxies for our benefit or place its black holes at convenient distances for our telescopes. The universe simply is a vast, self-consistent, ancient structure operating according to physical laws that evolved with no particular consideration for whether conscious beings would ever exist to observe them. And yet, we observe them, and yet they are to us wonderful. The wonder is not in the universe. The wonder is in us, in the capacity of the human mind to receive the universe's signals and transform them into meaning, into story, into the particular form of joy that arises when understanding deepens. This capacity, the ability to look at a number like 66 billion solar masses and feel something beyond mere arithmetic, is one of the most interesting and mysterious things about consciousness. It suggests that consciousness is not merely a calculator, not merely a survival tool for managing threats and resources. It is also a receiver, a resonator, something that, when it encounters the right signal from the universe, vibrates at a frequency we call wonder. TON 618 produces that signal. But why should scale alone produce wonder? Why should bigness matter emotionally? A grain of sand is not less beautiful than a mountain in principle. A moment of human kindness is not less significant than a billion years of cosmic history. The world of the small, of cells and molecules and quantum particles, is no less astonishing than the world of the large. The double helix of DNA, the precise orbital geometry of electrons, the quantum entanglement of particles separated by enormous distances. These are wonders no less extraordinary. Perhaps the reason scale produces such a particular kind of wonder is that it disrupts our ordinary sense of self. In everyday life, we are the right size. We fit. The world is built around our dimensions. The doorways we walk through, the chairs we sit in, the faces we look into at conversation distance. We are calibrated by evolution to the scales of the human world. And this calibration is so pervasive, so constant, that we cease to be aware of it. We forget that being our particular size is one specific option among billions. When we travel in imagination to the scale of ton 618, when we genuinely try to hold the fact that the event horizon of this single object is larger than the entire solar system, something happens. The ordinary calibration is disrupted. The self that is just the right size is suddenly, briefly aware of its own contingency. We could have been smaller. We could have been larger. The universe operates across dozens of orders of magnitude, and we happen to exist at one particular level of that vast spectrum. This disruption, this temporary displacement from the comfortable scale of the human world, is what we call perspective. And perspective, when it is genuine, tends to produce a subtle but real shift in how we relate to our ordinary concerns. Not an erasure of those concerns, not an invalidation of them, but a change in their weight, their urgency, their proportion. People who spend their professional lives working with cosmic scales, astronomers, cosmologists, physicists, often describe a particular quality to their experience of the world. A kind of habitual awareness that the ordinary is embedded in the extraordinary. That the city they live in, the problems they are working on, all of it is happening on a small rock circling an ordinary star in the outer suburbs of one galaxy among 2 trillion. This is not nihilism. It is not the assertion that nothing matters because the universe is vast. On the contrary, it is often accompanied by an increased appreciation for the specific, the local, the immediate. When you understand how rare a living planet might be, you look at a tree differently. When you understand how brief a human lifetime is against cosmic timescales, you are perhaps more inclined to attend carefully to its moments. The perspective of scale does not diminish the ordinary. It frames it, and framing changes everything. The philosopher of science Carl Sagan spent much of his career working to communicate this perspective, to share the view from the cosmos with as many people as possible. He believed with deep conviction that the scientific understanding of the universe was not merely a technical achievement, but a humanistic one. That knowing where we are, understanding the scale of what contains us, was essential to a mature civilization's relationship with itself and with the cosmos. His pale blue dot photograph and the meditation it inspired remain decades later among the most powerful pieces of science communication ever created. In a few hundred words using one image, he managed to capture something that is difficult to articulate but easy to feel. That we are small, that this planet is precious, that our conflicts are trivial against the backdrop of space, and that nevertheless, or perhaps because of this, we have a particular obligation to care for each other and for the place we call home. This is the gift of scale, properly understood, not terror, not despair, not the cold comfort of insignificance, but perspective, and with it, the possibility of a wiser relationship with our own smallness. Ton 618 is a teacher in this sense. Not because it has lessons to impart, it has no awareness of us, but because confronting it, truly confronting the scale of it, does something to the mind that cannot quite be undone. Once you have tried to hold 66 billion solar masses, once you have understood that an event horizon larger than the solar system is a thing that actually exists in the observable universe, the ordinary world looks a little different. Not smaller, just appropriately sized. And there is a particular peace in that, a quietness that comes from knowing your place. Not as a diminishment, but as a fact. You are here. This is where you are. The universe is vast. You are a small, brief, conscious part of it. And from here, from this specific, unrepeatable vantage point, you can look out at all of it and think, I know this exists. I know where I am. I am in the universe, and the universe is, in the most literal sense, in me. That is enough. More than enough. It is extraordinary. There is one more piece of context worth sitting with before we begin our return journey to Earth. It concerns the word observable, a word that carries enormous philosophical weight when we use it in phrases like the observable universe. The observable universe is not the entire universe. It is the portion of the universe from which light has had time to reach us since the Big Bang, approximately 13.8 billion years ago. Because the universe has been expanding throughout its history, and because this expansion has been accelerating for the last several billion years. The actual distance to the edge of the observable universe is not 13.8 billion light-years, but approximately 46.5 billion light-years in any direction, giving a diameter of about 93 billion light-years. Beyond this boundary, beyond the cosmic horizon, the universe almost certainly continues. The current best understanding of cosmology suggests that the universe is either very much larger than the observable portion or perhaps infinite in extent. Depending on the precise geometry of space, whether it is flat, positively curved like a sphere, or negatively curved like a saddle, the universe may have a finite volume or may extend without limit in all directions. We cannot observe beyond our cosmic horizon because the light from those regions has not yet had time to reach us. And because the universe is expanding, some regions are receding from us faster than the speed of light. Not because they are moving through space faster than light, but because the space between us and them is expanding. Light emitted from these regions will never reach us. They are beyond reach. Not merely in practice, but in principle. This means that TON 618, vast as it is just one object in just one part of just one portion of what may be a much, much larger universe. The 2 trillion galaxies of the observable universe may be matched or exceeded by an equal or greater number in the unobservable regions beyond our horizon. There may be black holes even larger than TON 618 existing in those unobservable reaches, unknown and unknowable to us. This is a humbling thought, and also a liberating one. The universe is not required to end at the boundary of what we can see. Our instruments define what we can observe. They do not define what exists. The cosmos does not confine itself to what is convenient for our telescopes. What this means is that our journey today, as vast as it has been, spanning 10.4 billion light-years to visit the largest known black hole in the observable universe, is still, in some sense, local. We have explored a corner, an extraordinary corner, but a corner nonetheless. The full extent of what exists, if full extent is even a phrase that applies, may be beyond any measurement we will ever be capable of making. Some questions may be permanently beyond the reach of empirical science, not because we are insufficiently clever, but because the information required to answer them is physically inaccessible, beyond the cosmic horizon, in regions of space from which no signal can ever reach us. There is something quietly wonderful about this. Science is not a project that will eventually be completed, with all questions answered and all mysteries resolved. It is an ongoing engagement with a reality that is larger than our ability to fully capture it. Larger than our instruments, larger than our mathematics, larger than our imagination, however far we stretch it. The universe will always be larger than our understanding of it. And this is not a deficiency, it is an invitation. The cosmos extends beyond our sight. The questions extend beyond our current answers. The journey extends beyond any single voyage we can make, however long. And yet, the journey is worth making. This one, everyone. Because every step taken toward understanding, every measurement, every model, every equation refined, every image captured, is a step taken by the universe toward knowing itself. And that, in the end, is what we are here for. Not to conquer, not to catalogue, not to reduce the mystery to a solved problem, but to witness, to understand, to be present with full attention to the extraordinary fact of existing in a universe this vast and this strange and this beautiful. We began with a breath and a quiet room and the weight of a body against a surface. We end there too. But something has changed. The room is the same. The body is the same. The breath is the same. And yet, for having made this journey together, the context has expanded. The ordinary space around you now contains, as it always did, the full depth of the universe. The stars, the galaxies, the filaments, the voids, the black holes, the quasars, the ancient light. All of it is out there, beyond the walls of wherever you are. And you know it is there. That is everything. We have spoken often on this journey of emptiness, of the vast distances between stars, between galaxies, between the filaments of the cosmic web, of the silence of space, the cold and the dark, and the absence of matter in most of the universe's volume. But it is worth spending a moment with the nature of this emptiness, because it is not, in fact, truly empty. Interstellar space, the space between stars, is not a perfect vacuum. It contains the interstellar medium, a thin, diffuse mixture of gas and dust, ionized particles and neutral atoms, magnetic fields and cosmic rays, and photons traveling in all directions. The density is extraordinarily low by human standards, typically less than 1 atom per cubic centimeter, compared to the 10 to the power of 19 atoms per cubic centimeter in the air you are breathing. But it is not nothing. Intergalactic space, the space between galaxies, is even more rarefied. But it too contains matter. The warm, hot intergalactic medium, a diffuse plasma of hydrogen and helium, and heavier elements that was ionized in the early universe and has never had the opportunity to cool and recombine. Much of the ordinary matter in the universe resides in this diffuse intergalactic medium, not in stars or planets. When we look at the night sky and see the brilliant points of stars and the glowing disks of galaxies, we are seeing the luminous minority. Most of the ordinary matter in the universe is invisible, spread across the vast spaces between galaxies. And then there is dark matter, the mysterious substance that makes up about 27% of the universe's total energy content. Dark matter does not emit light, absorb light, or interact electromagnetically. We know it exists because of its gravitational effects. It curves space-time, deflects light through gravitational lensing, holds galaxies together by contributing mass that the visible matter alone cannot account for, and shapes the large-scale structure of the cosmic web. But we do not know what it is. We do not know whether it consists of one type of particle or many. We do not know whether it interacts with itself or with ordinary matter through any force other than gravity. Decades of experiments have searched for dark matter particles directly. In underground laboratories shielded from cosmic rays, in detectors at particle accelerators, in observations of astronomical phenomena, without yet finding a direct detection. Dark matter remains one of the deepest mysteries in physics, and dark energy, the even more mysterious form of energy that makes up approximately 68% of the total energy content of the universe, is responsible for the accelerating expansion of the cosmos. Discovered in 1998 through observations of distant supernova, Dark energy behaves like a property of space itself, an intrinsic energy density of the vacuum, pushing space apart everywhere and always. As the universe expands and ordinary matter and dark matter become more dilute, dark energy becomes increasingly dominant. The future of the universe, whether it will expand forever, eventually cool and darken, or experience some more dramatic fate, depends on the nature of dark energy, which we do not yet understand. So, the emptiness of space is not emptiness. It is full of things we do not yet understand. Dark matter and dark energy, interstellar gas and cosmic rays and magnetic fields, the ancient photons of the cosmic microwave background radiation, permeating every cubic centimeter of the universe. We have explored enough to know that we are surrounded by mystery, that the space between the things we can see is full of things we cannot yet see. This is one of the great themes of the history of science, the discovery that apparent emptiness conceals richness and complexity. The empty space of classical physics, which Newton thought was an inert, featureless backdrop to the action of forces, turned out to contain quantum fields that vibrate with zero-point energy. The empty space between atomic nucleus and electron, which early models of the atom imagined as simply vacant, turned out to be full of quantum probability waves, virtual particles, and electromagnetic fields. The apparently empty space between galaxies turned out to be threaded with dark matter and filled with diffuse hot gas. Every time we have looked carefully at the spaces between things, we have found that they were not empty. The universe, in every direction, at every scale, is more full than it appears, more complex, more interesting. This is something to carry with you, the world around you. The ordinary air of the room you are in, the apparently featureless space between you and the ceiling, the dark sky outside, is full of fields, full of photons, full of neutrinos passing through everything without interacting, full of dark matter moving silently through the earth and your body without leaving a trace. The universe does not stop at the visible. It extends into dimensions and forms of matter and energy that we are still, slowly, learning to detect and understand. The emptiness is an illusion. The universe is everywhere. Before we return fully to Earth, let us pause one final time, not to look outward, but to look backward, to look along the axis of time rather than the axis of space. The light we use to observe TON 618 left its source 10.4 billion years ago. At that moment, life on Earth had not yet begun. The solar system did not yet exist. The sun had not yet formed. The nebula from which our solar system would eventually condense was still drifting, unassembled through the interstellar medium of what would become the Milky Way. We are seeing TON 618 as it was before the Earth existed. When that light left TON 618, when the quasar blazed at its peak and photons poured outward in all directions across billions of light years, there was no Earth to receive them. They traveled. They traveled for 10.4 billion years, through the expanding universe, through intergalactic space, through the forming and reforming structures of the cosmic web. They traveled through the epoch of the first stars and the first galaxies. They traveled through the long middle age of the universe, the period of quieting quasars and maturing galaxies, and slowly assembling chemical complexity. They traveled while the sun formed, and while the planets formed, and while the earth cooled, and while life arose in the oceans, and while cells learned to make oxygen, and while complex multicellular life evolved, and while animals crawled onto land, and while the dinosaurs arose and died, and while mammals diversified, and while our ancestors climbed down from trees and began to walk upright, and while humans learned to speak and to build and to dream. They traveled while all of that happened. And then, some years ago, in the context of 10.4 billion years, the most recently, those photons arrived at a telescope, a radio telescope, perhaps, or an optical telescope, or an instrument sensitive to ultraviolet light. They were captured by a detector. They were transformed into electrical signals. Those signals were recorded, analyzed, processed, and interpreted by scientists. And the result was a number: 66 billion solar masses. This is the extraordinary chain that connects the ancient light of Ton 618 to the minds of human beings on Earth. The light itself is one link. The telescope is another. The physics of general relativity, developed by Einstein a century ago, is another. The decades of observational astronomy that established the techniques of reverberation mapping is another. The training and dedication of the scientists who performed the analysis is another. And the chain extends backward through all of human science, through all the people who built the telescopes and developed the mathematics and asked the questions and trained the next generation of researchers. This chain is one of the most beautiful things humanity has ever built. It is invisible. It exists as knowledge and technique and understanding, not as a physical structure. But it connects the present moment to the ancient universe. It allows a creature on a small planet to weigh a black hole 10.4 billion light-years away. The universe made us out of stars. We turned around and learned to weigh the universe. There is a reciprocity in this, a kind of cosmic conversation carried on across billions of years of time and billions of light-years of space between the universe and its one known instance of conscious self-awareness. The universe sends light. We receive it, we think about it, we share it with each other. The conversation is ongoing, and so, with that thought, we begin our quiet return. The universe opens around us as we travel back through the filaments and voids, back through the galaxy clusters and superclusters, back through the expanding web of Laniakea, back toward the familiar glow of the Virgo supercluster and the local group, back to the Milky Way's soft spiral embrace, back through the starfields of the Orion Arm, back to the solar system, back to the warm yellow light of our ordinary sun, back to the pale blue arc of Earth against the dark. Home. The air is cool. The room is familiar. The breath is quiet. And somewhere 10.4 billion light-years away, an ancient black hole bends space-time in the dark. You know it is there. Welcome home. We began with a breath, with the weight of a body against a surface, with the smallness and intimacy of a quiet moment in a familiar place. And we end, or rather, we return to the same place, changed. Not changed in any dramatic way. Not filled with existential dread or paralyzed by the insignificance that such journeys might, in theory, produce, but changed in the quieter way that genuine understanding always changes us. Changed in the way that happens when you look at something you thought you knew. The night sky, the word large, the concept of distance, and discover that it contains depths you had not previously explored. The universe is large. We have said this many times in the course of this journey, but let us say it one more time, differently. The universe is not merely large in the way that a mountain is large, or an ocean is large. The universe is large in a way that exceeds every category of largeness that our language was built to describe. It is large in a way that requires new categories, new frameworks, new humility about the limits of intuition. And within this incomprehensibly large universe, there is an object, Ton 618, that is itself an extreme. The most massive gravitational object in the known cosmos. A black hole that would swallow the entire solar system. A gravitational singularity that has been bending space-time for billions of years. An ancient, patient, monumental presence in the universe. And we know about it. We measured it. We described it. We traveled there in imagination, and we looked at it from the outside and thought carefully about what it is. This is what human curiosity looks like at its best. Not the desire to conquer or exploit, but the desire to understand, to see clearly, to describe honestly, to share the view with others who could not make the journey themselves, so that the understanding spreads, so that the universe's self-knowledge grows. There is a philosophy implicit in the act of doing this kind of science communication. It says, the universe is worth understanding. It says, you deserve to know where you are. It says, the truth about the cosmos, however vast and humbling, is more beautiful than any comfortable falsehood. It says, small does not mean insignificant. We are small by every measure of size. We are brief by every measure of time. We are located in an unremarkable part of an unremarkable galaxy, in an unremarkable corner of the observable universe. By all quantitative measures, we are as negligible as anything could be. And yet, we wonder, we question, we build telescopes, we write equations, we launch spacecraft. We spend decades studying a single galaxy's center, perfecting our measurements, refining our models. We take the pale blue dot seriously as a home worth caring for. We tell each other stories about the universe, around fires and in lecture halls and in videos on the internet. This wondering, this irrepressible, persistent, sometimes impractical, always deeply human act of looking up and asking why is the thing that makes us remarkable. Not remarkable in the sense of being cosmically significant, as if the universe owes us importance. Remarkable in the sense of being extraordinary, of having done something surprising and unprecedented. We have become the universe's way of knowing itself. TON 618 does not know it exists. It has no awareness of its own immensity. It does not experience the space-time it bends, or the matter it consumes, or the light it distorts. It simply is. It obeys the laws of physics, as it always has, as it always will, without reflection or intention. But you, sitting wherever you are, having traveled with us across 10.4 billion light-years in imagination, you know it exists. You know something about what it is. You carry that knowledge now in the neurons of a brain that evolved from simpler organisms over hundreds of millions of years, on a small planet orbiting an ordinary star in a galaxy of hundreds of billions of stars. The universe, through you, knows a little more about itself. Isn't that extraordinary? The night sky is not just beautiful, it is a record of history. The history of the universe, written in light that has traveled for billions of years to reach your eyes. Every star you see is a sun. Most of them have planets. Some of those planets may have life. One of them, just one, so far as we know for certain, has life that looks at the sky and wonders about what it sees. That life is you. That planet is Earth. That sky is your sky. Look at it when you can. Look at it with the understanding that you have now, of what it contains, of how far it extends, of what waits at its most extreme distances. Look at the faint smudge of Andromeda in the northwest. If you are in the northern hemisphere on a dark autumn night, look at the Milky Way, that band of light that is your own galaxy seen from inside. If you are somewhere dark enough to see it, look at the moon, remembering that human beings have stood there. And somewhere in the direction of the constellation Cairns Venatici, invisible to the naked eye, at a distance your mind now has some framework for approaching. 10.4 billion light-years, as it was when the universe was young. Something immense and ancient and dark bends the space-time around it, as it has for billions of years, as it will for trillions more. You know it is there, it cannot know that you know. But that asymmetry, that extraordinary, beautiful asymmetry, in which a speck of matter in the universe can know and contemplate and wonder about the largest thing in the universe, is perhaps the most remarkable fact of all. Welcome to the universe. You have always been here. Now, slowly, you are beginning to see where here is.